We'll have questions at the end, but if you have any clarification questions, you can ask them right away. But if they are of more technical or philosophical nature, please keep them towards the end. And yeah, with that, please join me in welcoming Professor Martha White, who's going to tell us about policy gradient methods as approximate policy iteration. Take it away, Martha.
Okay, thanks, Abhishek. I'll start off by saying that there's some loud construction noises outside my house right now sometimes, so they're very temporary. I'm sorry if it starts happening again. I'll pause or do something if it happens. Okay, great. Otherwise, I'll also say that this is not a talk about polished work. It's more a talk full of questions. So it's for us to discuss this topic a little bit more, and I'll give you a little bit of insights that we have for a recently submitted paper. Okay, so 20 minutes is a really short time. I'm going to try to go through reasonably quickly, and what I'm going to try to do is give you the needed background, because I know not everyone in this seminar knows all the things about policy gradient and RL. So I'm going to try to introduce to you what policy gradient is and how it can be seen as approximate policy iteration. And then I'm going to try to get you to understand a little bit about why this view is useful. So it might let us think a little bit about new algorithms, and maybe lets us think more about how we can prove soundness of existing algorithms. And as I'll repeat throughout, this view is absolutely not new. There's a lot of people right now talking about mirror descent and policy gradient methods. And actually there's a lot of older work also thinking of policy gradient as API. But I suspect to a lot of us in this group, it is sort of new. So I'm going to cover some of the basics and then talk about the specific thing we focused on. Okay, and here I'm going to assume you do know RL. So I'm going to assume you know some of the basics of policy iteration and that you actually have seen policy gradient methods, even if you don't know them in depth. Okay, so first, the assumptions for the setting I'm going to be looking at is I'm going to be looking at the episodic setting. I do care about function approximation, so I can put that on the slide as well. And I'm going to mostly focus on continuous actions, even though a lot of the same ideas apply to discrete action. And actually, I'd say for some of the insights about policy gradient, many of them have been in the discrete action setting, which ends up making it the question we tackled less interesting. So we're going to ask a lot about how do you do approximate gratification, and that becomes a lot more interesting in the continuous action case, which has a less understanding. Okay, so what's policy gradient? First, I'm going to tell you what is policy gradient, and then I'm going to tell you what is approximate policy iteration. So in policy gradient, we usually look at this episodic objective, and our goal is to get the policy that has the maximal value and expectation starting from the set of start states. So we have some start state distribution D0. We're going to sample start states S from there, and we'd like to find the policy that has the most value from those start states. Okay, and so we have this nice policy gradient theorem that tells us how we can actually take the gradient of this objective. It's a surprising theorem, actually, because if you look at this objective and think about it a little bit, it could become complicated. So it's sort of nice that we end up having this pretty simple form for the gradient that just says the gradient corresponds to taking the gradient of the policy weighted by its action values. And when we're looking at the states starting in the discounted future state visitation under pi. Okay, so I'm not going to say much more about that gradient. Actually, what I'm going to say instead is, even though we have this nice gradient, actually most implementations of, let's say, policy gradient methods don't really seem to actually use this gradient, and yet they seem to perform well in practice, actually. So most actor-critic methods drop particularly the weighting out in front. So I mentioned this d pi theta that tells you how you should weight your states, and it's according to discounted state visitation. Okay, most of these methods just ignore that weighting, and there's a few papers that sort of highlight that when you do ignore that weighting, it introduces bias, and in some cases, it just means that your policy gradient isn't actually a gradient, and most of those are from Phil Thomas. And then we have a paper in this group, me and Hassan and Eric, about how if you do drop that weighting, in some cases, you can converge to really bad solutions. And maybe we just have one counterexample that shows that this can be bad. Okay, so if they're not really using this gradient, what are they actually doing? So what it looks like they're actually doing is policy iteration algorithms. So policy iteration, to remind you, is the sort of dance between value and policy. So we're going to we're going to start with some policy, then we're going to go up this line. I think you can see my pointer. Yeah, we're going to go here. We're going to go estimate the value for this policy. Then we're going to gratify that policy to get a new policy pi. Then we're going to go estimate the value for that policy, get to a new value function. We're going to iterate this process until we reach V star and pi star, the optimal policy. Okay, in practice, we're going to do approximate policy iteration. And for that, we don't actually need to do these two steps to completion. So we'll start from some policy pi, we'll step towards where the true value function is for that pi, but not all the way. And then we'll greetify earlier before we reach V pi. And then maybe we won't even step all the way to, the greedy policy and so on. So we'll have this approximate policy iteration where we can both compute approximate values and we don't have to fully greetify either. Okay, so what we usually see in practice is sort of two settings for this. These arrows were harder to move around than I would have thought. Anyway, so we often either see the first case, which is we do approximate value updates, and then we do exact greedification. So that sort of corresponds to this picture. We don't fully go to V pi, but we always go get the greedy policy with respect to our current action value estimates. So you can sort of think of this like star. So I've also put politics under here because I think that it fits nicely into this category. Chad can disagree with me later if he thinks. And then there's also this other category where we think about having exact value updates and approximate greedification. Okay, and that there isn't a lot of algorithms that really technically do this, but a lot of theory for policy gradient methods, I would say, are doing this, where they're reasoning about if I had the gradient with the true V pi or Q pi, what would the behavior of my algorithm look like? Okay, and so there are fewer methods doing, but the methods in practice are actually doing something more like this. So I'm going to tell you why that is, and then tell you why you should care. Okay, good. Okay, so first, what does it actually mean to do approximate greedification? Okay, so in policy gradient methods, really what we're doing is maintaining explicit policies. So we're going to learn these parameterized policies, and for this greedification step and approximate policy iteration, I'm going to say what it means to do approximate greedification. Okay, so there's sort of two options people often use to do greedification in the first place. You can either act perfectly greedily with respect to Q, as in you're going to go pick the max action, the best action you possibly could. So that's option one. So you're going to say, I'm going to have this deterministic policy pi. It's always going to go take the greedy action. Okay, and then option two is to do a soft greedification. So here we're going to still keep a stochastic policy, but we're going to do this greedification where we use a Boltzmann distribution. This Z is normalization function, so you can kind of just ignore it. So proportionally, we're going to be sampling according to these action values. Okay, and this policy pi is going to be concentrating, it's going to increase the probability of actions with high action values, and it's going to decrease the probability with low action values. And this choice of tau is going to sort of tell us how narrow we make that greedification.
A quick question, Martha. For option one, those argmax, right, as opposed to max?
Yes, argmax, exactly.
Thank you.
Thanks, Russ. Yeah, exactly. Yeah, so politics is an example of using a soft greedification. And a lot of methods currently use a soft greedification strategy, typically when we're doing these entropy regularized things. Okay, so for either of these settings, an issue when we're doing parameterized policies is might not actually be possible to do either of these two things exactly when we maintain a parameterized policy. So here I said pi of s is equal to, or pi dot of s is equal to. Now that won't always be possible, and instead we're going to try to estimate this parameterized pi theta that, depending on whichever setting you might be in, we're going to be focusing on the second setting. We're going to try to approximate that greedified policy. You might ask, why are we approximating this thing? Why don't we just do the explicit thing? So, politics does, many methods just go ahead and compute this and just use it. Or maybe we just go ahead and compute the greedy action according to Q. Okay, so the reason mainly for me is that in continuous actions, this becomes more problematic. So, computing the max action for Q when you have continuous actions is itself a hard optimization problem. So if instead we had an explicit policy that we could sample from instead, that can be much less expensive. And even this stochastic Boltzmann Q distribution policy can be really expensive to sample from. So again, if we had a simple policy that was sort of distilling out what it thought was the best actions, then we would just be able to do better in continuous actions in terms of computation. There could also be other reasons as well that I've listed here. Okay, so our goal is to get this explicit policy because we're not going to be able to use these fully exact policies. So instead of just using Q and then always computing pi implicitly from Q, we're going to maintain this explicit policy that's going to try to estimate these things. So now our question is, how are we going to estimate these explicit policies? So how are we going to get a pi theta that approximately equals this Boltzmann Q distribution? Okay, so this is commonly already done, and the common thing to do is to use a KL divergence. So we have a distribution. We'd like to match, let's say, for example, this exact distribution here. So we have this Boltzmann distribution over Q. That's our ideal thing that we wish we could have. It's our pi star, let's call it. No, pi star was bad terminology. It's not the true optimal policy. What I mean is it's the exact gratification policy that we want on this step. So for the given Q, if I could, I would use this. I can't because I've decided I'm going to use explicit policies and I want to avoid having to compute that for continuous actions. Instead, I'm going to sort of try to estimate it with a parameterized policy. So we could use a KL divergence since we have probability distributions. And whenever we talk about using KL divergences, we can talk about the two different variants. We can talk about a forward KL divergence and we can talk about a reverse KL divergence. So actually in our work, we focused a lot on this question. Like once we got to the point of we'd like to do approximate gratification, already this was a glaring question that was open to us. Which of these two choices would be better? Yeah, which of these two choices would be better? And it's really not obvious up front which of the two choices would be better. So now let me explain how these two things might actually look different, just to see why the choice might actually matter. And so did I say anything else? Or maybe I'll say one other thing is that for this reverse KL, if you actually look at the difference between our parameterized policy pi theta and the exact gratification policy, it ends up looking like this term here. So this term has no effect. We can just ignore that normalization term. And here we just have what looks a lot like the regular, policy gradient objective, which says, I'd like to make this value large. The way to make it large is to increase probability of actions with high value. And then we had this additional entropy regularization term. I feel like Chab unmuted himself maybe to ask a question, but maybe not. All right. So just as an example of how these two things might look different, just taking a plot from one of our results, we designed this very simple little problem. But in that problem, we were checking, how do the two different KLs, what is the outcome policy if I use one of these two KLs? Okay, so let's imagine the blue line is the target distribution. So it's that Boltzmann Q distribution we're trying to approximate. And it has this bimodal structure. You can't really see the blue line behind the screen line, but it's also there as well. Okay, and we restricted our policy so that it can't model bimodal distributions. It was a unimodal Gaussian. So it sort of has to hedge its bets. It can't perfectly minimize this KL. And in this situation, there's two very different solutions from these KL divergences. So the yellow line is using the forward KL, and forward KL is usually described as being mean seeking. And that's exactly what's happening here. It doesn't want to have zero probability on this part because that means it would be very different from the distribution. So it kind of just puts its mass more flat across everything. And the reverse KL is mode seeking, so it doesn't really mind that it's completely ignoring this part of the distribution. It's going to focus all of its probability on the highest mode. I will say that in our actual experiments, this only happened a few times. Most of the times, the difference between these two things is actually not as big as we thought it was going to be. But in any case, you can see how this choice might actually result in different parameterized policies, and that's sort of the question we're trying to answer. Okay. So let me go back to the point that I was trying to say, though, which is we were trying to talk about how are policy gradient methods well thought of as approximate policy iteration, and then what are the implications. Okay, so I'm just going to look at one of these KLs. Let's look at this reverse KL. Do I have 5 minutes? Like I have 5 minutes before to leave enough time for discussion. Anyway, so for this reverse KL, if you look at the gradient of it, what you'll see is you have this gradient term here that you likely recognize. And if we set tau to 0, so if we say I'm not going to do any entropy regularization, that's this term here. So if tau is 0, this part disappears and we're just left with this term over here. So remember, we're minimizing KL because we want to make the two policies similar, which is the same as maximizing without this negative here. Okay, so then I just pasted here again what the actor-critic gradient looks like, and this inner term is the same as this term, except, this Q has a specific choice. The Q should actually be the Q pi theta. Okay, and so actually if you start looking at lots of different algorithms out in the literature, many of them can be well thought of as either mainly minimizing or reverse KL with or without entropy regularization, where the most maybe obvious one is with actor-critic, where we said Q is equal to Q pi. Now, one of the things here I haven't mentioned is this d pi theta, so this weighting out in front. I haven't told you anything yet about what this weighting should be, but I'm going to keep going. Okay, and like I said, with soft gratification, so with tau greater, we're just adding some entropy regularization. Okay, so now the reason this is now a nice thing to do instead of having to try to directly compute, for example, that Boltzmann distribution, is that it's actually straightforward to sample this gradient. So even though, trying to compute this full distribution is hard, we can actually slowly iterate our explicit policy towards being something that looks like that, or at least concentrates actions around high probability actions. Okay, I'm gonna keep going. Yeah, 5 minutes, I'm gone. So one other thing to note here is I'm sort of leaving out the other categories of methods. There's kind of 4 variants here. There's reverse KL with and without entropy regularization. There's forward KL with and without entropy regularization. There's actually a lot of algorithms out there that have used some variant of reverse KL and actually also some that have used forward KL. And in our paper, which maybe I'll get Alan and Sungshu to share, we've sort of tried to categorize all the methods into those 4 different quadrants. But I'm not going to have time to tell you about all of those. Okay, but one other choice that's important for us is for function approximation. We don't just want to say within one state, how am I going to greedify my policy? I need to make choices across all states. So if I want to, concentrate probability on good actions in one state, it might mean that I don't get to do as much concentration on good actions in another state. That's what function approximation is going to give us. So we're also going to have to make a choice when we look at this approximate greedification on what distribution D of S we're going to use over states. Okay, so implicitly when our agent is actually computing all these KLs, it's going to pick some set of states and it's going to do gradient descent from those states. A very common choice to do is to have a big replay buffer, just grab some transitions and states from that replay buffer, and to do approximate greedification. So compute these KL divergences from those states. But I do think we need to ask ourselves, what's the right choice for D? What would be a good choice for D? And is that the right choice for D? Arguably, the weighting suggested by the policy gradient theorem is actually to use a discounted state visitation instead. Okay, so sort of putting this all together, when we are thinking about policy gradient as approximate policy iteration, we sort of just have these 3 steps, which sort of correspond to several choices. So we can sample some states from, let's say, a mini batch, or from we can sample some states from replay buffer or from some other strategy for sampling states. Then we're going to update our action values with whatever your favorite algorithm is. So in that approximate greedification step, I didn't tell you how you would approximate your Q. I just said, given that someone has approximated Q, our focus is on how do we do that greedification, the approximate greedification. Okay, and then the final thing is to do your policy update, and that's what we're calling the greedification step. And that's where you're going to use the gradient of the KL from S, either using forward or reverse KL, or hard greedification or soft greedification. Okay, I'm going to actually skip this experiment because we don't have time. But now I want to get to the point of all of this. So why is it useful to think of policy gradients this way? So why is this approximate policy iteration be useful? So just to be clear about what was said on the last slide, we are sort of alternating between estimating action values and then doing greedification. Okay, so whenever we look at the policy update for our policy gradient methods and they look like a greedification step, then they could be well interpreted as doing approximate policy iteration. Okay, so one of the reasons I think this view is useful is it maybe gives us a different way to understand what policy gradient methods are doing that are not actually implementing the policy gradient itself. Okay, so for example, if you're not actually choosing D to be D pi as is needed for the policy gradient theorem, maybe instead you could see the algorithm as doing approximate policy iteration where it has chosen a D according to how it wants to allocate function approximation resources for approximate greedification. And then we could try to interpret the algorithm on that lens rather than interpreting it as it's not using a true gradient and has a biased gradient. Okay, and the other reason I think it's sort of useful is that there are just so many policy gradient methods out there right now. I think it's nice to be able to break it up into these components that are sort of key components, and we can ask what's important for the weighting, what's important for what we choose for the KL, you know, should be forward or reverse, and is entropy regularization helping or not? Rather than asking specific things like, is soft actor critic better than actor critic? There's really only one key difference between them. Okay, another reason I think it's useful is almost all the algorithms use a forward KL divergence when they are doing this approximate gratification. And I think one of the reasons is simply because actor critic has been one of the more popular methods, and it is implicitly using a reverse KL. But you know, some of our own experiments suggested that the forward KL actually has lots of promising properties. Okay, and the final reason I think that it could be useful to be thinking about it this way is hopefully it could give us alternative theory to understand these methods better. Because right now there's actually kind of a lot of negative results in the sense that, you know, for example, is policy gradient actually implementing a gradient? It really isn't a gradient-based method. And so that's sort of a negative result of what the algorithms are doing. Yet we do see them do nice things in practice. So maybe there's some way we can show soundness by considering this alternative way of thinking. Okay, let me just say the last couple of things. So let me see. I've left myself insufficient time. Okay, maybe I'll summarize these next few slides quickly. Okay, so maybe what I should say is what our actual goals are. So our goals are to say, when we are doing this approximate gratification step, it isn't really all that well understood, and we'd like to understand it better. So the way that we try to understand it is to look at it, ask the question, should we do a forward KL, should we do a reverse KL, and what is the impact of entropy regularization or not? Okay, there's actually a lot of theory that already tells us something about what choices would make sense for this. Okay, and one thing I'm going to highlight, I'm going to leave with this point, is there's a lot of the recent results reformulating policy gradient methods as mirror descent. And they're actually adding one additional thing that I didn't mention, which is they're doing a conservative gratification. So I'm going to skip that, and I'm going to come to these questions. But in that step that I mentioned where we do the approximate gratification, where you take an entropy regularization plus what looks like the typical actor critic update, there's also an additional component you can add when you do that policy update, and that's to say don't go too far away from the previous policy. So you also add a KL term between the new policy and the old policy. Okay, so we didn't talk at all, we didn't look at conservative gratification at all in our own work, but a lot of this mirror descent literature suggests that adding this additional conservative term is also very important. So sort of what I wanted to leave off in this discussion is there's lots of these recent insights that assume conservative gratification, and there's actually some statements from particularly Gergely that say that conservative gratification is key. So here I said TRPO is greater than A3C. What he's saying there is that TRPO has this conservative component, A3C does not have this conservative component, and they can say nice things about TRPO, but they can't really say anything about A3C, and in fact there seems to be at least some examples where it doesn't look like it converges to any stationary points. So to see the discussion of today, what I really would like to talk about is when we are looking at this gratification step, what does our current theory say? What do people think about the need for having conservative gratification? And what do we also think about when it comes to these weightings, when we're using the weighting of D in our gratification? A lot of the theory currently requires D to be D pi, but I think once we start looking at this as just a function approximation trade-off that says, I want to do more gratification in this state versus this other state, it's less obvious to me that it has to be D pi. You know, imagine you have a really awesome function approximator that can get all the states, can gratify across all the states, then why should we need to have D be equal to D pi? And yet I don't actually see any work that says that we have good convergence results when D is not equal to D pi. Okay, I'll end there so we have at least 5 minutes to have a discussion.
Well, thanks, Martha. The floor is now open for people to contribute to the conversation. And there's a couple of points in the chat that I would like to point out. The first of which was, so you're talking a lot about a forward and reverse scale. Is it something that makes scale divergence more interesting than other types of distance metrics? For example, there's a symmetric one, which is Jensen-Shannon divergence. And so maybe why would people not consider that? Have they considered it, or is there something bad about it?
That's a good question. I don't know if there's anything bad about it. We considered Kale simply because we were trying to understand the properties of what people are doing. And most people seem to be using this reverse Kale. So that's sort of where we started, and then asked, well, what would happen if you did the most simple next step, which is to use a forward Kale? I think there are some nice properties of the two, the forward and the reverse. The fact that the reverse is mode seeking, I think, can be nice because it says, I don't need to know about all the complexities of the action value. I just need you to concentrate on the most high valued actions. So you can get these really simple policies. At the same time, there also seems to be some evidence that the forward Kale helps you in terms of exploration. A paper from this group by Amii and others, Jin Cheng, seems to suggest that the forward Kale really helps a lot with exploration. So then a different divergence again could have other properties. This is where someone else could chime in and see if they have any thoughts.
Yeah, like I feel like they're just the simplest choices, which doesn't necessarily mean that they're the best choices. So you could do something like Wasserstein, right? But then you'd have to do a little more to think about how you're going to optimize that.
Okay, so Martha?
Yep.
So since you mentioned TRPO, and you mentioned gratification, I feel like since all the methods that we are discussing currently, they are first order methods, which means we just calculated the gradient. And then the step size is important. So this is one thing that could mean like how much greedy you are. And the other thing is the direction that you move towards. And just like if you do second order methods, then the direction that you move towards would be different. And also when you have like you have some entropy term, the direction that you move is also different. So so I feel like the things might be related to like more fundamental things like step sizes or the exact methods that you are considering.
I think maybe what you're saying is the optimization procedure is important, and the optimization surface is going to impact how these methods behave. Absolutely. I'm not sure exactly what you're asking, but if we were to say about differences, say, between the reverse Kale and the forward Kale, there's definitely optimization differences between those, where one of the reasons the forward Kale could be also promising is that it seems to have a smoother optimization surface. This is sort of the slide I skipped here, where we tried to look at what is the optimization surface for these two things in a really simple setting, where we just have a bimodal distribution, one state or no states, however you'd like to think about it, so a banded setting. And we definitely found that it was more problematic to optimize the reverse Kale. That's important. But a lot of this really nice theory out there right now is assuming sometimes exact steps and just asking if I were to actually get these full solutions, what would be my stationary points? And already there's, I suppose, some negative results or difficulties. This Bayard paper that I have cited here is pretty crazy. You should go read it. It's sort of trying to summarize all the methods out there as with this one algorithm that they're introducing.
Thank you.
You're welcome.
So I have a cool, I don't know if it's a question.
Yep.
It's I'm trying to understand this whole area, and I want to say it's like an alternative to following the policy gradient. That approximate policy iteration, as you described it, would be an alternative. And so, which kind of makes your talk title, contradictory or something. Policy gradient methods as approximate policy iteration. It's really an alternative
I think
because you could, yeah.
So the idea, would you mind turning down your volume or muting? Thank you. Okay. I think at least very clearly shown, especially by these mirror descent papers, is that a lot of these policy gradient methods really can be seen as doing it for like lift and project step. So it is still a policy gradient strategy with mirror descent, but it looks a lot like, okay, what am I saying here? Is it an alternative? Okay, let me say different. I'll say it from the way they were looking at it, actually, because I don't know that mirror descent worked well enough to say what they're saying. What we're saying, at least what I'm saying, is that each of these gratification steps looks like a policy gradient update. It looks, say, for example, just like actor critic or soft actor critic. And then so in that sense, it's actually a generalized view because the action values themselves could be set to Q pi. But they could also just be approximate action values like you would do in policy iteration or approximate policy iteration. And then what you can do is use theory from the policy gradient literature. Like, for example, policy gradient theory does tell us something about how this approximate policy iteration methods are going to work, because already we know if there's a bad stationary point in the policy gradient setting, then we're going to be stuck in the same bad stationary point here if we're going to do full exact value estimation and then go to this gratification step, because the gratification step is exactly a policy gradient step. It is at least my claim.
So just to add to that, I typed this into the chat as well, but I might as well say that so we know, for example, in tabular case, if you take natural policy gradient, it becomes this Boltzmann or soft greedy version of policy iteration. So there is a continuous spectrum between policy gradient and policy iteration, it seems. And it's not like that it's a binary alternative, but it's like you can be somewhere on the spectrum. And I'm sure that there are a lot of other algorithm designs which can also travel between like exact gratification and policy iteration and policy gradients. And so then, like, the question becomes, where do you want to be? Like, what is a good choice? Why this? Why not that? And it seems to me that one idea that comes up time to time in the literature is that if you have functional approximations, you have to tolerate errors. Then you don't want to do these harsh gratification steps. So somehow you want to soften things. And all of these methods are trying to do that in different ways. And the policy gradient on its own, because it's an incremental, like let's just change the parameters a little bit with the step size, is also kind of doing that in a way, right?
So I guess the spectrum for policy gradient methods to policy iteration is that extreme where something is not approximate or it's not policy iteration would be something like reinforce, because no values are being estimated. Like you're truly estimating, you're trying to get this unbiased estimate of that policy gradient. And then as you start estimating value functions, I think it really does put you on this spectrum towards approximate policy iteration. Habit degrees.
Yeah. I mean, if what I meant is that if you're making incremental changes to your parameter vector, then you're not, like making a full step of gratification anyways. So policy gradient methods with their incremental updates are, incremental, like, but not hard in any sense policy iteration methods.
They're not doing a full gratification step.
It's not full gratification. Yeah, it's
exactly. I think by nature, all policy gradient methods are typically doing this kind of approximate gratification. Because otherwise, you're going to probably go and compute that closed form. For example, just go get that Boltzmann Q if you want to do your full gratification. I do think the other point that Chaba raised, though, is still how you choose to view this on that spectrum. Like, how should we be looking at it? Like, is it useful to think of it as policy iteration? Is it more useful maybe to still think of it as policy gradients? That's kind of one of the things I wanted to discuss a little bit. It does seem like a lot of the theory, what is the theory that we have for approximate policy iteration? You know, some of this new theory is definitely taking a gradient descent view because it's using a mirror descent view. And it's now saying lots of nice things about these algorithms. So arguably the view that they're just regular gradient descent strategies is a good one. But I think the other direction is that it sort of precludes other ways of trying to analyze it. Like if it isn't exactly a mirror descent strategy, you know, some of these papers say if you don't have this weighting d pi, then this relationship is gone. Or, you know, some of Phil Thomas's work, like I said, where you don't really have the gradient of an objective. Maybe that means that there's a limit to that view. And now we need to think, well, is there something else we can say about these methods? They could still be sound. They could still converge to some kind of stationary point, but they aren't really gradient methods in the traditional sense.
We are over the official time, but feel free to stay back and continue the discussion. But folks who want to leave can do so now. Thank you so much for attending. And this was our fourth and final talk of the week. We'll have 4 more talks next week. And we plan to have like a social sort of this thing tomorrow. And more details of that will be posted soon. So yeah, stay tuned and see you next week.